So let's now have a look on a case study on how sort of doing the whole iteration. So here is an example of a typical performance analysis cycle that you go through iteratively. So you first measure the performance of a program, identifies the bottlenecks, identifies the cause of these bottlenecks, eliminates this call, and then you go through all these levels here. And you do it, you have to think on several levels here. You have to understand the problem domain, you have to understand the programming model, and you have to understand the hardware interaction. And if you use tools to do this, these iterations go much faster than otherwise. So let's look at this case study here. We want to compute the number of primes between 3 and So let's look at this case study to find where the task is to find the number of primes between 3 and 10 million. So we have a for loop between 3 and 10 million here, and for every number we try if it's a prime number, calling the function is prime, and if that is true, then we add the variable num_primes here. And then the is prime function is brute force algorithm. Just tries that whenever we find a number which is a factor in this program, then we return 0. Just assume that this is the fastest possible sequential version. It's not really, but let's pretend anyway. So let's see what happens. So first we compile it. This is with the Intel compiler. As I said earlier on, we turn off optimizations, and we use -G to allow for profilers to work more correctly. So we run this program. We find out that this is sequential code so far. Execution time is 8.7 seconds, of which the user, almost all is in user mode. All right. We use timing here to find the execution time in the is prime code only. In the is prime loop only, and we find about the same information as before. We can use the Intel amplifier to find hotspots. So we run the program here with the command line version of the amplifier, and we'll find, not surprisingly, that the is prime function, where we check the prime number, if a number is a prime number, is the hotspot, not surprisingly. It's also possible to group hotspot by source code line, but by default it provides information on the function level. So let's try what happens when we have higher optimization. We go to -03, not much difference. It takes still a long time. So that didn't help us a lot. Okay, let's parallelize this code now. Okay, we parallelize it with this for loop here, because checking each number for being prime or not is totally independent of the other one. That should be good, simple enough. 5.5 seconds instead of 8. Okay, execution time is reduced, but not much. But what's worse is that the number of primes found is now not correct. 663,813. It should have been 664,000. Okay, this is a problem. So suspect race condition. Use the inspector to find and collect data races. This is the code for finding data races. If you use the GUI version, it's more intuitive to use. Okay, it found a data race. Let's see information about this data race. This is the information we get. It's a little bit wordy, but basically it finds that there is a store, read, store on source code line 44, and if you look at source code line 44, this is where the num primes is updated here. So we protect the num primes with a critical, or atomic could have been used also in this case, and then we find that we get the correct value here, but still it's not very fast. We can check for race conditions again, and now we find that there are no new problems. It's interesting also to see here that the checking for data races is really much more time-consuming than sort of profiling in itself. But we have no race conditions, that's good. But the speed up is bad. We have a speed up of like less than 3 on 4 cores and less than 3.5 on 8 threads. This is now on a hyper-threaded quad-core processor, so we shouldn't expect a lot of speed up from 4 to 8, but up to 4 we should get close to 4, because this is almost perfectly parallelizable program. So let's use the profiler, the Intel amplifier, to find out CPU utilization for the 4 threads, and then we can see that different threads execute a lot different in time. We collect hotspots, but now we group by thread. So we find that thread 3 executes for 3.4 seconds, thread 2 for this amount of time, and so on. We have load imbalance. Can we get better CPU utilization? Well, we can use some knowledge from the application domain and understand that the number of primes not exceeding x is asymptotic to x log x, meaning that prime numbers are not evenly distributed. The higher number, the farther apart are the prime numbers. So let's use dynamic loop iteration scheduling instead. So this is the parallel loop. Instead of using the sort of pragma ohm before without specifying the schedule, let's use dynamic with 500 iteration chunks. And now we get the yellow line here, which is much better than before. So we now get between 3.5 and 4 here, which is not perfect, but it could be good enough for us. And now when we check the load balancing again, we can see that we are more or less equal. A good load balance here.